Biomedical engineering is a very diverse field. Things from wearable sensors through to artificial hearts to how we interact with machines, the subject of all sorts of disciplines involved. My particular research focus is in medical imaging and medical devices, so I'd just like to take 10 minutes and talk you through a couple of projects in that space and finish with a rather large project and one of our major directions for the future. So as Simon mentioned, in the past we've came up with some inventions that have been incorporated into magnetic resonance imaging systems. And I'm very proud to say that now over 8 billion patients have been scanned using that technology. And the group of people involved in it have really had an influence on radiological practice over the years. I'm going to talk a little bit about how some of our work has changed government policy in the UK in one of the projects we've been working on there, and that's quite interesting. As Australians, a very small country internationally, we have very deep pockets of expertise, and it's important that we recognise that, so much so that the Europeans have sought us out to do this sort of work. And next two speakers you will see are very well internationally connected. And then I'm going to finish up with our projects for the future. So for those of you who haven't experienced a magnetic resonance image or haven't seen one or haven't had the claustrophobic, loud experience of being in one, and I can see that some of you have, this is what an MR image looks like. It has exquisite soft tissue detail, different to CT scans, which are very good at visualizing bones, for example. MRI's exquisite detail of all sorts of soft tissue throughout the body. But we don't only have anatomical detail recorded in these scans, we get functional sort of information as well. So this is an MR scan that is sensitized to blood flow. So you don't necessarily see the anatomy, but the blood flow. And these are our carotid arteries in our neck, interior and exterior, and bifurcate. One of the early indications of stroke risk is plaque buildup in such arteries, and this is a routine scan now using MRI. So the point is that it is a multifunctional modality. And we're able to image in any plane, in any dimension, through any organ, at any angle, and we can image very rapidly. And here's just an indication of some of the quick fly-throughs that neuroradiologists can look for to look for very gross abnormalities. This is typical MRI technology. Here, for those of you who haven't seen a scanner, 1.5 Tesla. Tesla is the strength of the system, the magnetic field strength. And one of the developments that we've been working on here at UQ in collaboration with our spin-off, one of our spin-off companies, Magnetica, that has now spun off into a life of its own, is to develop technology that is much smaller and well-defined towards the clinical application. So this is an extremity imaging system that images joints in the body, and you can see it's a much more pleasant experience. You get a pretty radiographer to talk to you while you're having a scan, which is always a good thing. Whereas lying in this is quite a claustrophobic and a loud experience. So we at UQ designed the superconducting magnet in this technology together with Magnetica. That's been licensed now through a Japanese colleague to General Electric, who've installed 220 of these worldwide to date. These are the sort of scans you can get from them: a wrist scan, ankle, elbow, foot and ankle, knee. And this started as a part of a PhD project into optimization mathematics. And so the course of the progression from that project through the engineering to a commercial product is a really important pathway. And as I said, they're out there in the field at the moment. These are the sort of blown up pictures that you can get. And coincidentally, once we had this sort of technology working and these sort of images were available, and this is a sagittal scan through the knee, that's your kneecap there, and this white stuff here is the articular cartilage on the joints, the patellofemoral joint there. And osteoarthritis and acute injury injures that, and you can detect it very clearly. Other manufacturers then became interested in these sort of scans and said, well, are you able to pull out maps of this cartilage, and could we use that as a biomarker for things like osteoarthritis or sports injury. And so even though it was a GE system, Siemens were interested in doing this. And we now have a project with Siemens where we extract cartilage from these images in the dedicated imaging systems, provide a map, and then we also use some mathematics to test how normal that three-dimensional map is using statistical shape maps and spherical harmonic variations. So strange things happen through the course of a research project into commercialization. I mentioned the European connection, just a couple of slides on that. So a directive was put out a few years ago, around 2007, from the European Union in Brussels, setting a limit for induced current in any worker in any application at particular frequency ranges. And this came to a surprise to the magnetic resonance image community and aluminium smelter industry and any others that use strong magnetic fields, and our colleagues in CERN using accelerators. So anyone who walks past a static magnetic field or who is exposed to a static magnetic field that is changing even slowly will have current induced in their body because we're really an agglomeration of conductors. And this was a regulatory limit set to that. But it turned out that the limit was such that it meant that no one could ever have an MRI scan. No one could work around aluminium smelters. There was outrage in Europe amongst the community, but the European Union wanted third party removed from Europe to do some studies. And at that time, there was no way to measure the fields that workers were exposed to or to model it effectively. So we ran a project for a couple of years and developed a small device that you could put in your pocket, similar to an ionizing radiation tag, that was able to measure static magnetic fields over a shift. So we could record exactly the exposure that workers were getting, and then we could model it. We developed three-dimensional models of the body that talked about the electrical properties of the body, and then moved them around aluminium smelters, the CERN accelerators and MRI machines, and lo and behold, we found out that these red bits here were above the limits prescribed by the European Union, and so no one could walk around an MRI scanner or take a patient into it. Subsequently, after this report, that changed the legislation. So we're very pleased to say we've had that impact in Europe, and that has followed through to Australian regulation as well. The final thing I'd like to do is to look forward to the future. So these are MRI scans of a patient with a lung tumour. This is the tumour here. It's quite a large tumour. Liver is obviously the lung, the diaphragm, and the liver. This is another view of the same tumour. So if I drew a circle around that tumour and held that constant, which I have difficulty doing, you can see that whatever position I choose, the tumour will move through that circle. And that's how radiation therapy works. So it assumes that the tumour is fixed in place and a treatment plan is made to irradiate the tumour and give it as high a fractional dose as is possible. But it can't account for tumour motion. It does a fixed plan at a fixed moment in time. It necessarily, the clinicians, the radiation oncologists, then make the plan very wide because they know the tumour will move, and so do we. And you can see the tumour moving a couple of centimetres easily. So what then happens is that healthy tissue is irradiated necessarily, and that the tumour itself doesn't get high enough dose that it needs for treatment. So patients have to go back for repeated treatment. Healthy tissue continues to be irradiated, and eventually the tumour gets a high enough dose. So our plan is to change that and do image-guided therapy, where we have a radiation device, therapy device inside an MRI system. The MRI system finds the tumour, tracks it, feeds that information back to the radiation beam, which then irradiates only the tumour and irradiates it with a very high dose. Now, our clinical colleagues estimate that this will improve survival rates in lung cancers by as much as 25% if we can get it to work the way that we do, and reduce potential side effects by up to 75% in these patients. So that's our motivation over the next 5 years. We have enough funding to get about halfway at the moment, so we continue to search for funding for this project. And this is another view of a different tumour through the heart. And you can see that the motion is quite complex and through plane. It's not linear motion. It's very difficult to predict. There's the tumour there. So our idea is to develop a new sort of magnetic resonance technology where the system is split, the patient lies in the middle, and we have the radiation device here. So we have funding to develop some of the technology, and this is the insides of some of the technology. Superconducting coils, minus 269 degrees Celsius. Coils that enable spatial localization of the image. And then we need a number of peripheral devices to monitor the well-being of the patient and to feed that back to a radiation therapy device, which is highly magnetic. Okay. And so integrating those two systems together is a major challenge. If you let a spoon go near an MRI machine, it could kill someone. It accelerates so quickly into an MRI machine. The magnetic fields are so strong, so it's a major challenge to get those two things to work together. But we believe we know how to do it. And one of the challenges is we have to develop tracking software. You have to be able, in an MR image, to find something in that image and track it. And that has to be done in real time. We have to be able to do that several times during the breath cycle. And so we've developed prototypes of this so far. And this is a motion tracking software picking up one of the kidneys, just as an example of how it is done. So I've talked a little bit about our work in the past, about our impact on global policy in Europe and our projects moving forward. So thank you very much for your attention.